In support, we're going to be talking about prime factorization. So the first thing you're going to ask yourself is, why the heck are we learning this? So prime factorization is going to be a big tool that's going to help you a lot whenever we start simplifying radicals in Algebra 1, which is actually what you'll do today. So prime factorization is simply the factoring of numbers using only prime numbers. Okay? And remember, prime numbers are those numbers that are divisible by 1 in itself. So the numbers we're going to be using is really only up to 13. If not, I have not seen an example we're going to have to use a number higher than 13 that is prime. Okay? So, again, what are factors? Okay, factors are any number that when multiplied together give us another number. Okay, so if I have 6, I know that 2 and 3, when I multiply 2 and 3 together, give me 6. More factors of 6 are 1 and 6, because I can multiply 1 times 6 and I get 6. Okay? So before we talk about prime factorization, let's just talk about factoring. So let's find all the factors of 16. So if I have 16, what two numbers can I multiply together to get 16? I know that I can multiply 1 and 16 together to give me 16. Are there anything else? I know I can multiply 2 and 8 together to give me 16. Is there more, though? I can multiply 4 and 4 together to give me 16. So I know that the factors of 16 are 1, 2, 4, 8, and 16. Now you may ask yourself, why did I not write 4 twice? Because 4 is a repeating factor. It means that it's multiplied by itself to give me 16. So I'm not going to write that twice. So my factors are 1, 2, 4, 8, and 16. So whenever I talk about the prime factors, all that means is that I'm looking for the prime numbers that are factors of 16. So remember, prime numbers are those that are divisible by 1 in itself. So the only prime factors of 16 that I have are 1 and 2. So 1 and 2 are my prime factors of 16. Okay? Now I went through that kind of fast because that should have been a little bit of review. So now we're going to talk about the prime factorization. And whenever we do prime factorization, we're going to use this thing called the upside down ladder method, which I will get into in just a second. So whenever we do prime factorization, we're starting with 16. The first question I'm going to ask myself is, what prime number can I divide in this case 16 by? So what prime number can I divide 16 by? So remember, my prime numbers are 1, 2, 3, 5, 7, 11, 13, and that list goes on and on forever. So what prime number can I divide 16 by? The only one that I have is 2. So I have 16 divided by 2. Once I find that, 16 divided by 2 is 8. And I'm going to ask myself the same question. But now, instead of 16, what prime number can I divide 8 by? Again, it's 2. 8 divided by 2 is 4. And again, this process gets very repetitive. What prime number can I divide 4 by? Again, it's 2. So I see that I have 2 at the end. I know at the bottom of my ladder that I'm finished when I have a prime number at the end, okay? So I have 2 at the end, which is a prime number, so I know that I'm done. So whenever I am finished, to clean it up a little bit, I can come through and any number that is boxed in, 4, 8, and 16, I can simply cross out. So I know that the prime factorization is going to be these numbers on the outside of the ladder. So I have 2, 2, 2, and 2. So the prime factorization of 16 is 2 times 2 times 2 times 2. Okay? If there's any questions, pause and message me on It's Learning, and I will be able to help you out. Okay, so moving on. These are some examples that I would like you to work. So pause the video, work these 3 examples, and then you can watch me work them. Okay, so here we have 48. A common theme you're going to see is that we're going to be dividing by 2 at the start. And oftentimes you're going to be able to do that whenever it is an even number. It's a safe bet. Okay? So I'm going to divide by 2. 48 divided by 2 is 24. Again, I can divide by 2 because it is an even number. So I have 24 divided by 2, and that is 12. 12 can be divided by 2 prime numbers. It can be either be divided by 2 or 3. It does not matter which one you pick. It is simply personal preference. I'm going to pick 2. So 12 divided by 2 is 6. Again, we have the same situation. I can divide 6 by either 2 or 3. I'm going to pick 2 again. It's been working well for us, so we can keep using that. Okay? Lastly, I have 3 at the end after I divide 6 by 2. 3 is a prime number. So again, I can come back and I can cross out these numbers that are in the boxes. So my prime factorization is going to be these numbers on the outside of the ladder. So that's going to be 2 times 2 times 2 times 2 times 3. Okay? So moving on, we have 75. So this is the first instance where we haven't had an even number to start with. So what prime number can I divide 75 by? I know that 75 is a multiple of 5, so I can divide by 5. 75 divided by 5 gives me 15. What prime number can I divide 15 by? Again, I have 2 choices here. I could either use 3 or 5. I'm going to choose 5. And that's going to leave me with 3. Again, as in our last example, 3 is prime. So I know that I'm done. So I'm going to come up here and I'm going to cross out these numbers inside the boxes. So my prime factorization is 5 times 5 times 3. So 5 times 5 times 3. Now, what if I would have used 3 here instead of 15? Because I have the same opportunity at the beginning. So I can have 75. I'm going to divide by 5 again just for simplicity. So I have 5. I still have 15 here. Sorry, I'm losing track of my colors. So I still have 15. if I divide by 3 instead of 5, I'm still going to get 5 at the bottom. 5 is still a prime number. And I still have my prime factorization. 5 times 3 times 5. And I can rewrite this to make it look exactly like my first answer here, because these are the same thing. Okay? So now, my last example, I have 180. 180 is an even number, so I'm going to divide by 2. $180 divided by 2 is going to give me 90. Divide by 2 again because it is even. Next, I have 45 after I divide 90 by 2. So what prime number can I divide 90 by? I have options here. I can divide by 3. I can divide by 5. I'm going to choose 5. I'm going to divide by 5. Again, as we saw in our last example, if you have the opportunity to use multiple numbers, it doesn't matter which one you pick, okay? So this should be a 5, not a 2. So I'm dividing by 5. 45 divided by 5 gives me 9. What prime number can I divide 9 by? 3. When I divide 9 by 3, I'm left with 3. Again, as in all of our examples, 3 is prime. So I know that I'm finished. So I'm going to come back and I'm going to mark out these numbers that are in these boxes. So my prime factorization are these numbers that are on the outside of my ladder. So I have 2 times 2 times 5 times 3 times 3. Okay? And again, I can write this in any order. So I have 2 times 2 times 3 times 3 times 5. Okay? So if you have any questions about prime factorization, make sure you reach out to me on It's Learning. The next topic we're going to talk about is identifying like terms. Now, this is something you have seen before. We talked about like terms back in Unit 2 whenever we were adding and subtracting polynomials. When you're combining or adding and subtracting polynomials, you can only combine like terms. Okay, so talking about the polynomial approach, if we look at problem A, if we're identifying the like terms, the thing that's going to tell us whether or not they're like terms are the variables and their exponents. So the first term in polynomial A is 2. 2 is a constant. So the like term with 2 has to be another constant. So I'm looking through here. I have 2, I have negative 7x, I have positive 6x to the fourth, I have 3x, and I have negative 2x squared. Of those, I do not have a constant, so 2 does not have a like term. What about negative 7x? So that is a linear term. It has a variable and an exponent of 1. So my like term with negative 7x has to be another linear term. I know that 6x to the fourth is not a linear term. It has an exponent of 4. Okay? But I see that 3x is a linear term. It has a single variable of x and an exponent of 1. Lastly, I look at negative 2x squared. It is not a linear term. So my only two like terms are negative 7x and 3x. Okay? So moving on. The first term I have is 5x. Again, 5x is a linear term. So, for something to be a like term with 5x, it has to be a linear term. Okay? So I have 5x. The next term is 6. 6 is a constant. 6 is not a like term with 5x. 2x. That is a like term with 5x because it is a linear term. So 5x and 2x. And then I have a negative 7x squared. For something to be a like term with negative 7x squared, it would have to be an x squared term as well. I do not have another one of those. So the only two like terms in my second example are 5x and 2x. Okay? Are there any questions about that? If there is, please pause, message me on It's Learning, and I'll get back to you as soon as I can. Okay, so the reason we did all that is to say this. With dealing with radicals, we're going to have like terms just like we just had. Okay? So whenever we're talking about radicals, we have three parts to a radical. We have the index, and that's this number on the outside of the radical symbol. So I just answered my second question. This is the radical symbol. Okay? And the number under the radical symbol is the radicand. All right? So, the index is always going to be a positive integer. It will never be negative. So if that index is not there or it's imaginary, then the index, or in this number here, is going to be equal to 2. Okay, this is known as a square root. Okay? So we did all that to say this. For radicals to be like terms, they have to have the same radicand. So if you want to rewrite this as they have to have the same radicand, you can say they have to have the same number under the radical symbol. Okay? So, I'm going to move on and look at some examples. So, it says, let's look at an example, identify the like terms. So again, the question I'm going to ask myself is, if they're like terms, is what numbers are the same under the radical? Symbol. Okay? So I'm looking through my terms. I have 3 root 5. 5 is under the radical. 2 root 3, 4 root 12, and 78 root 5. So I have 5, 3, 12, and 5 again. We're not worried about this number or these numbers outside of the radical symbol. We're not worried about that. They don't really do a whole lot for us. So like I said, the only thing we're focused on are these numbers here under the radical. So I can see that I'm going to do in purple that my like terms are going to be 3 root 5 and 78 root 5 because they both have 5 under the radical symbol. Okay, it's a pretty easy concept to grasp, but it's very important whenever we're going to get into adding and subtracting radicals. Okay, so now we're going to do an example. I want you guys to work these, so pause the video and identify the like terms in these three examples. Okay, so again, what numbers are the same under the radical? So I have 22, I have 3 root 17, and 4 root 17. I can see in yellow, I have 2 17s under the radical. So 3 root 17 and 4 root 17 are going to be like terms. So let's look at the next one. Root 5, 4 root 5, and 4 root 5 again. Okay? I can see I have 5 under the radical in all three terms. So I know that these are all like terms, simply because I have a 5 under the radical symbol in all of my terms. So the last one, I have root 62, root 183, and root 48. I do not have any numbers that are the same under the radical in any of my three terms. So I have no like terms in this last example. Okay? So that wraps us up for Algebra 1 support today. If you have any questions, please reach out to me. Do not hesitate to ask me questions about Algebra 1 or Algebra 1 support. I'm here to help you, so please reach out, and I hope you all have a good day, and I'll see y'all soon.